All right, to wrap up this unit, we're going to look at some of the most common types of patterns you're going to see in mechanisms. We're going to put names to them so that you can recognize them in any sort of reaction that we come up against. And then we'll kind of end on doing a bunch of examples. We're going to combine a lot of these common steps together so that you might not even know what the reaction is, but all you have to do is recognize what you start with and what you end with, and be able to recognize what happened with the bonds. And you should be able to draw up a pretty accurate mechanism without ever having even seen the reaction before. So the first pattern we're going to look at is something known as nucleophilic attack. And we've already addressed this in part, where I just never really put a name to it. But this is just simply a nucleophile making a bond to an electrophile. So a nucleophile uses its electrons to make a bond to something positive. And we've done a lot of these examples before. Like, for example, in the acid-base chapter. So here we have our base. We know that bases use their electrons to form bonds to hydrogens, but this is going to be our nucleophile. Now, why is that the nucleophile? Well, that nitrogen's got a lone pair on it. It's got a partial negative to it. And this is why we're going after the hydrogen, because that hydrogen in that relationship between the oxygen and the hydrogen is partially positive. Now, as I told you in the acid-base chapter, I can't leave it like that. I'm forming the bond between nitrogen and hydrogen, but hydrogen can only have one bond to it. So I'm moving the electrons in that bond back to the oxygen. And that oxygen's got three lone pairs around it. Remember, that's one of our trends for formal charge. And then the nitrogen has got four bonds to it, no lone pair. So that's the common pattern for nitrogen having a positive charge. Another example, I think, that we highlighted earlier. Hey, let's get some practice with this. What's our nucleophile here? What's the negative thing? Well, that's the thing with the full negative charge here, the bromine, or the bromide ion, I should say. And what's our electrophile? Well, we got a carbocation. So I'm going to make a bond between the thing that has electrons and the thing that wants them. All right, let's kind of take this from a different direction. Here's the overall reaction here. And I want you to pause the video and ask yourself what bonds got formed and what bonds were broken. Okay, so now that you've done that, let's identify, first of all, what is the nucleophile in this reaction? Well, I have something here that's got a full negative charge. Now, what's our electrophile here? Well, in this carbon-oxygen bond, the oxygen is highly electronegative. That carbon is going to have a partial positive charge. So there's my electrophile. And if this follows the trend right up here, nucleophile making a bond to an electrophile, then let's do that. Here's where my bond is forming from that oxygen to that carbon. Just going to get rid of this here real quick. Now, if I look at my product, notice that I do not have a pi bond here. So my mechanism has to address that. These pi electrons are going to move up to the oxygen. I know I have to do that also because if I didn't do it, I would have 10 electrons around that carbon. Right? And then finally, let's look at this reaction. Now this one's a little bit more difficult to spot the nucleophile because there isn't anything polar and there's nothing with a formal negative charge. But in that list of nucleophiles that I gave you in the previous lecture, we know that pi electrons are commonly used as nucleophiles. And the hydrogen makes a pretty decent electrophile because of that hydrogen bromine polar bond. Hydrogen partially positive, the bromine is partially negative. So I'm going to draw those pi electrons forming a bond to the hydrogen so that I don't violate the octet rule for hydrogen, or not necessarily the octet rule. Hydrogen only wants one bond to it. So I got to break that bond between hydrogen and bromine and move the electrons back to the bromine. Now, as you can see here, one of the carbons got an extra hydrogen on it, so its formal charge is just fine, but the other one is missing a couple electrons around it, so that's why there's a formal charge there of +1 on that carbon. Now, another common pattern you're going to see a whole lot is the loss of what we call a leaving group. Now, what is a leaving group? This is a little facetious, but it's a group that leaves. Okay, I'll use Lg a lot to kind of represent a generic leaving group. But I'll go a lot more in depth into what makes a good leaving group in another chapter. But just to kind of highlight so far, like the best leaving groups are the ones that are stable after they leave. Meaning once they leave, they're pretty happy on their own. And so, for example, like halides are great leaving groups, like bromide, iodide, chloride. Those are very stable ions in solution. Water is a very common leaving group. I mean, think about it. Water is super, super stable. I mean, our lives kind of depend on it being very stable. Um, Ions that are resonance stabilized, like for example, this kind of ion, are just, I don't know if I've used R as a symbol yet. R is just a generic carbon group. Could be one carbon, could be 50. It's just what we use when we don't want to show a big chain of carbons. But that ion, once it leaves, it's pretty stable on its own because it's resonance stabilized. So let's take a look at some examples of what the mechanism looks like for a leaving group leaving. So here's the overall step. And ask yourself, what happened here? Well, that carbon bromine bond is no more. So how do I demonstrate that mechanistically? Well, the way I break a bond is I start at the bond and I move the electrons towards the bromine. And this is an example of a leaving group leaving. I could have gotten really generic here and just used Lg, and that fits right into this template. All right, well, let's look at another example. Okay, now I want you to look at this template right here. What does that look like to you? What is HOH? That's water. Water's a great leaving group because once it leaves, it becomes water. So I'm going to break that bond between the carbon and the oxygen. Since the electrons left that carbon, it becomes positively charged. The electrons went to the oxygen, and so now the oxygen has a formal charge of 0. Now, quite often, leaving groups leaving are combined with other steps. So let's take a look at this example here. We're going to take hydroxide, react it with this compound to make an alcohol. and Br minus. Now, let's go through our exercise of first of all identifying what happened here. Okay, so any bonds forming. Well, it looks like there was a bond formed between OH and this carbon. You see that right there. So carbon to OH. And any bonds broken? Oh, we got this bond between carbon and bromine, and now those electrons are on the bromine. So let's deal with the bond forming part of this. I'm going to use the electrons of oxygen to make a bond to that carbon. Can I leave it like that? If I did, I would violate the octet rule for carbon. So I have to break this bond and move those electrons back to bromine. Now, what was that? Look at this first arrow. I'm going to call it number one here. What is arrow number one demonstrating? What kind of mechanistic template? Number one is demonstrating nucleophilic attack. And what is arrow number two here demonstrating? Arrow number two is demonstrating a leaving group leaving. So it is quite possible and quite often you will see that we're going to combine a lot of our templates into one mechanism or even into one mechanistic step. All right, let's kind of look at one more kind of cool example before we move out of this. And we'll take some time to draw. All right, once you've copied this down, I want you to pause the video and I want you to look at what happened here. I want you to notate everything that is different down to the very, just to the simple bonds. I want you to make a note of what is different between the reactant and the product. Okay, so now that you've had a chance to look at it, one of the major things that's different is the chlorine has left. Okay, but is that the only thing that has happened? We just kind of take a look here. We got some, new stuff happening right here. There's some new stuff right here and some new stuff right there. Okay, so let's draw some arrows that demonstrate all of that new stuff. So let's start off at that oxygen with the negative charge here. Notice that between the nitrogen and the oxygen, there is a brand new pi bond here. So let's draw an arrow for that. Boom, right there. Now, that's not the only thing that has to happen because that puts way too many electrons around nitrogen. So let's address how did this pi bond come about? Because it was just a single bond here. Well, I'll use these pi electrons here to form that new pi bond. Well, I can't violate the octet rule. If I left it like that, there'd be a carbon that'd be very unhappy. So finally, I'm going to move these here. And notice that gets me this pi bond here. And again, so that I don't violate the octet rule for this carbon down here, I'm going to show one more arrow showing my chlorine, the leaving group, leaving. And so notice like this is a reaction that we probably won't even specifically talk about this reaction until like next semester, this specific reaction. But you don't need to even know what it is to be able to draw a mechanism for it because all you have to do is recognize what bonds were broken, what new bonds were formed. Just ask yourself what happened, and you use curved arrows to demonstrate and describe the answer to that question. Now, another common mechanistic step are proton transfers. And we have done a lot of this already with Bronsted-Lowry acid-base reactions. That's what a proton transfer is donating a proton and something accepts a proton. That's the textbook definition of a Bronsted-Lowry acid-base reaction. And in a sense, this is a form of nucleophilic attack, where the electrophile is a proton. Now, you're not always going to see H plus specifically, but you'll typically see hydrogen bonded to something else. So in this case here, we have an alcohol and hydronium. Hydronium's got protons to donate. You learned that back in general chemistry. OH, that oxygen's got a lone pair. That's a pretty basic or good basic site. And so the base will use a lone pair to pick up a hydrogen so that we don't violate the octet rule. We'll move those electrons back to oxygen. And this is exactly the same two steps we would do in our acid-base chapter. All right, let's look at another one here. And this time, what I want you to do is I want you to look at the whole thing and then ask yourself what happened. All right, so one major thing that had to have happened is I'm forming a bond between an oxygen and a hydrogen. And then I'm breaking this bond here between the hydrogen and that oxygen. So let's draw a mechanism that demonstrates this. And again, this should be reviewed because this is just an acid-base reaction, a Bronsted-Lowry acid-base reaction. So I'm going to use the lone pair on this oxygen to pick up a hydrogen, makes a bond to that hydrogen, and this bond has to break so that hydrogen only has one bond around it. Now, let me switch this up a little bit. I'll use this same carbonyl here, but this time I have hydroxide here. Now, in the previous problem, this was acting as the base, and hydronium here was the acid. But what's the base in this last step, or in this, I'm sorry, this last example? This is our base, and this is our acid. Remember, hydrogens alpha to a carbonyl are slightly acidic. So I'm going to use a lone pair on the base to make a bond to a hydrogen. Can't leave it like that though, because that would put too many bonds to hydrogen. So I will move those electrons back to this atom. And just to kind of review, remember we said the reason why this hydrogen on an sp3 carbon is a little acidic, or I should say a lot more acidic than a hydrogen on a normal sp3 carbon, is because it's resonance stabilized. So I can draw a resonance form. No, I'll just draw the arrows in here. That move that charge to another atom. Now, finally, the last common pattern in mechanisms are rearrangements. And there are many different types of rearrangements. Probably focus on some um, either this end of this semester or beginning of next. But right now, we're going to focus on what are called carbocation rearrangements. Now, in the past, we've seen carbocations. We've talked about them a little bit. We haven't really identified or gone in depth into what they actually are. Okay, so a carbocation is a carbon missing a pair of electrons around it. Has six valence electrons with a positive charge. Carbocation is sp2 hybridized, so it has a trigonal planar shape. That's very important to remember for later. And where the positive charge comes about is that the p orbital, the unhybridized p orbital, is empty. I want you to think about that because there's such a common mistake that students make with carbocation rearrangements. You cannot use an arrow to move a positive charge. Why is that? Well, a plus charge is just an empty, I'm going to kind of, here's our p orbital there. It's an empty p orbital. Can you move anything that's empty? No, there's nothing to move. So a carbocation is the absence of electrons, or is the result of the absence of electrons. You can't move the absence of something. You can fill it up, so you can draw an arrow to a carbocation, but you never, ever, ever, ever can start your arrow at a plus charge because there is nothing to physically move. Now, let's take a look at the different types of carbocations. So the first one we'll look at is just what we call a methyl carbocation. And then if there's one carbon attached to the carbon with the plus charge, let me fix this a little bit. We call that a primary carbocation. If there are two carbons attached to the carbon with the plus charge, we call that a secondary carbocation. And if there are three carbons attached to the carbon with the plus charge, we call that tertiary. Now, I want to highlight something here is that when I talk about carbons attached to the carbon with the plus charge, I'm just looking directly adjacent. Okay, like for example, this carbocation here only has one carbon directly attached to it. So we call that primary. I don't care about this other stuff. Oops. I don't care about all that other carbons attached because it's not directly attached to the carbon with the plus charge. Now, one of the reasons why we notate these carbons differently is that they have a different order, or I'd say there's like a hierarchy when it comes to stability. So the stability increases as we add more carbons around the plus charge. So these are more stable and these are less stable. In fact, methyl and primary carbocations are so unstable they don't exist. You can't form them because they're so unstable. Secondary and tertiary, yeah, those are fine. We're going to see those a whole lot. Now, why does having more carbons around um, make carbocations more stable? And this deals with a concept called hyperconjugation. And that's what this diagram here represents. I'm gonna erase this and then I'm gonna put it back real quick. So how does a carbon close to a carbocation help stabilize it? Well, there's this kind of brief overlap between the sp3 orbital and the unhybridized p orbital of the carbocation. When those two molecular orbitals overlap, it's helping distribute that positive charge to more atoms. And so the more carbons around to do that, so let's say there was like another carbon over here instead of, well, maybe instead of a hydrogen, there was another carbon. Well, there's another sp3 orbital that can overlap with that unhybridized p orbital. So the more carbons there are directly attached to the carbon with the plus charge, the more that positive charge can get spread out. And that's what hyperconjugation deals with. Okay, so I'm going to draw this back again. So it's very important to remember the stability of the types of carbocations. Now that I've kind of laid the foundation for what a carbocation is, let's talk about how they rearrange and why they rearrange. Carbocations will only rearrange to become more stable. Here's an example of this. So here we have a secondary carbocation. That secondary carbocation says, hey, wait a second. If I look like right next to me, okay, I'm going to look directly adjacent. So that's like this carbon right here and this carbon right here. Actually, I'll use a different color for the other one here. So there. So that secondary carbocation says it looks at the green carbon, it looks at the yellow carbon, it says, wait a second, that yellow carbon, if I could move to that yellow carbon, I would be a tertiary carbocation. But this is what you don't do. Don't do that. Because what that arrow is showing is that that plus charge is physically moving. You cannot pick up a plus charge and move it elsewhere. What I can do is I can take a hydrogen with its electrons and move it over adjacent. Okay, so think about it like this. We got a hole here, like you dig a hole in the ground. Now, can you move that hole elsewhere? No, you can't move an empty space. But what I can do is I can take the dirt from something else and move it over here to fill this hole. And now I got an empty hole here and the hole that was empty before is now filled. That's the same way you do a carbocation rearrangement. I'm going to take a hydrogen with its electrons, and again, I can only move adjacent. I cannot go any farther than one carbon over. And so now this hydrogen's over here, and I have a more stable tertiary carbocation. The name of this type of movement is called a hydride shift. Okay, hydride is H minus, hydrogen with its electrons. This is not a proton. I'm not doing a proton transfer. I'm moving H minus, a hydrogen with its electrons, from one carbon to an adjacent one. Now, if you can't move a hydrogen, try moving a carbon. So I'm going to use a very similar type of example. But again, let's take a look at this carbocation here. That carbocation says, oh, I'm going to look to the right and I'm going to look to the left. If I look to the right to the green carbon there, that's no good. That's a primary carbon. I'm not going to become less stable. But if I could convince one of those carbons to move over on the yellow carbon, then I'd be tertiary. So that's what's going to happen. Notice on that yellow carbon, there are no hydrogens. So if I can't move a hydrogen, I can move a carbon. So I'll draw in the methyl group there specifically. I'm going to take that methyl group with its electrons and move it over one carbon. And so now I'll draw in the CH3 specifically. Now I have a tertiary carbocation, something that is more stable than secondary. Now, before I do some more examples of this, I want to highlight some kind of I don't want to say special cases, but some interesting cases. The key thing is you always go to something more stable. Never equal instability or less stable. Okay, so what do I mean by that? Let's take a look at this compound here. And I got a carbocation. If there is a more stable option, that carbocation will rearrange. Well, what are my options here? I look adjacent one direction, and I look adjacent in the other direction. Notice I have two hydrogens there. This carbocation is starting off secondary. If I were to do this, which it's a valid arrow, would that become more stable? No, I would be going from secondary to secondary. But if I were to do this, now I've gone from secondary to tertiary. I've gone more stable. And then finally, before we leave from carbocations, is carbocations can become more stable by being resonance stabilized. Now, remember how I kind of highlighted up here, oh, primary carbocations are so unstable they don't exist. I kind of was telling like a mostly truth, partial withholding the truth. There are instances where primary carbocations can be formed because they're resonance stabilized. So for example, something we call an allylic carbocation. Now, first of all, let me define what allylic means. Allylic is the first position right outside a double bond. So here's our pi bond. The first position over, the first carbon over, is called an allylic carbon. So if there is a plus charge on that allylic carbon, we call it an allylic carbocation. Now that allylic carbocation is resonance stabilized. So I can move those pi electrons over, and now the plus charge is on a different carbon. So this is about as stable. Some would argue maybe a little less stable, but for all intents and purposes, these are about as stable as a normal secondary carbocation. That's not resonance stabilized. All right, so let's do a little bit of practice here. And this is going to kind of summarize all of our common mechanistic patterns. So look at letter A, and what of our four patterns is A describing? Okay, well, first of all, I'm starting with a carbocation. And that hydrogen has moved over. We've done a rearrangement. So this is a carbocation rearrangement. Now, if you look at this, this is kind of, I'm going to go down a rabbit trail with this problem here. Why would this rearrangement happen? This carbocation right here is secondary. And this one right here is secondary. I'm kind of, aren't I like breaking my own rule I just said on the previous page? Like you don't go from equal stable to equal stable. You don't go from secondary to secondary. This one, though, is not just secondary. It's also allylic. It's resonance stabilized. This secondary over here is not resonance stabilized. So that's why that rearrangement would happen. So that's just a little rabbit trail, but kind of something important to note. Okay, so let's take a look at B. All right, now just because there's a carbocation there doesn't mean, this is a rearrangement. No, you have to look and see what happened. So if we look here, we have something that has electrons, like a nucleophile, and something that wants electrons, like an electrophile. This is just simply a nucleophilic attack. Okay, well, let's look at C. Now, with C, again, you might think of this, oh, well, you got a nucleophile, something has electrons, something wants electrons, but this is a specific type of that nucleophilic attack because this used to have a hydrogen on it, and now that hydrogen's over here. This is a proton transfer. Now let's look at D. Okay, what is that arrow describing? Well, I'm making a bond from this oxygen to this carbon. So what does that oxygen look like? That oxygen looks like a nucleophile. And that carbocation is a great electrophile. This is just a nucleophilic attack. And then with E, what's happening here? Well, the only arrow that I see here is this bond that's breaking. That chlorine used to be bonded to carbon, now it's no longer bonded. So this is just a leaving group leaving. All right, now finally, what we're going to look at is combining all of these mechanistic pathways together and being able to look at a reaction and try to come up with a plausible mechanism for what bonds are breaking and what bonds are forming. So we're going to be looking at mechanisms that have multiple steps in them. So take some time and copy this down. If you want to like fast forward a few seconds in the video, you can just do that and pause it. Okay, so what we're going to do, two things. We're going to identify which steps are involved, which are common patterns are involved in each of these steps, and then we're going to draw the curved arrows to demonstrate those mechanisms. So we'll start, oops, here. Okay, so what is happening in this first step? So if I look at kind of what's going on with this oxygen right here, it's got an extra proton on it. So there's a bond that was formed. And if I look at what happened to the bromine, well, the bromine is no longer bonded to a hydrogen, so that's a bond broken. So but the specific atom here that was transferred was a hydrogen, a proton. So this first step is demonstrating a proton transfer. An acid-base, a Bronsted-Lowry acid-base reaction. You should be masters at that by now. So I'm going to use the lone pair on an oxygen to make a bond to hydrogen. So that hydrogen only has one bond to it. I have to break this bond and move it back to the bromine. Now let's look at the next step here. So in the next step, what happened? And actually, it might be helpful if I drew the water here. There. Well, in the next step, I'm just focusing right here. Notice there used to be that HOH plus there. Now it's no longer there. It looks like a bond got broken between that carbon and oxygen. So I want to show that bond breaking. And this is an example of a leaving group leaving. Now, why is there a positive charge on that carbon there highlighted in green? Well, it used to have a full octet around it. And that water left, it took those electrons with it. There's two lone pairs on that oxygen. So it became a carbocation. Now let's look at the next step. Again, look very carefully at what happened. It looks like that carbon highlighted in green has a plus charge on it. And now, not only is that plus charge somewhere else, it looks like a methyl group got moved over. Well, what is that? What's going on here? That's a carbocation rearrangement. Okay, so I'm going to take that carbon I highlighted in yellow, and it's going to move with its electrons over one carbon. I'm just going to go adjacent. That's as far as I can go. Now, what is the justification for this? Well, this was a secondary carbocation. Now it's a tertiary carbocation. And finally, to wrap this up, what's going on in this last step? Okay, well, everything is happening kind of around here. There's a new carbon-bromine bond. Well, think about this. You got Br minus, and you got something that's got a plus charge. That's a really good nucleophile. This is a really good electrophile. So I'm going to make a bond from a nucleophile to an electrophile. This is an example of a nucleophilic attack. Okay, so let's take a look at this next example here. So just look at these first two arrows here. What's going on? Well, I got something that could be like a nucleophile, and this hydrogen could be an electrophile. But how will we get really super specific with this kind of nucleophilic attack? You got something here that's acting as a Bronsted-Lowry base, and something here that's acting as a Bronsted-Lowry acid. This first step is a proton transfer. The OH minus now has an extra hydrogen on it. I just transferred a proton from the acid to the base. Now, how would we label this next step? Okay, again, kind of focus on the arrows. Notice how we're making a bond here. From one of these carbons to that carbon of CO2. There's a new bond right there. Well, think about that carbon bond right there. You got oxygen, which is partially negative, carbon partially positive. Oops. You got a nucleophile making a bond to an electrophile. So this whole thing is demonstrating a nucleophilic attack. Now finally, let's look at this last one. Here we have something with electrons, something that wants those electrons, but I'm transferring a very specific atom here. I'm going from something that um, had a hydrogen on it, and it's giving that hydrogen up. So here we have OH. That OH now has a hydrogen on it. This is another example of a proton transfer. Okay, now let's kind of get like really into the more complicated, more complex problems. Drawing the mechanism for things that we haven't even covered yet, for types of reactions that we haven't talked about, probably won't talk about for, for weeks or for months. So how do we draw a mechanism for something we haven't seen before? Well, let's just ask ourselves what has happened. Okay, so pause the video. I want you to write down what you see is different between the reactants and products. Think about what bonds are breaking and what bonds are forming. Okay, so you've done that. Let's talk about bonds forming. Okay, what's new? Well, I have a new bond between this carbon and one of these hydrogens. That's this new one right here. So I formed a bond between carbon and hydrogen. How about bonds broken? Well, I broke the bond between the oxygen and hydrogen. Anything else that's different? I guess you can kind of put it in bonds broken. You lost a pi bond. Okay. So how am I going to address this? How am I going to form a bond between that carbon in yellow and that hydrogen in yellow? Well, the only thing I can use, because this carbon right here doesn't have any lone pairs on it, only thing I can use is the pi bond. I'm going to use this pi bond, and that's how, I'm addressing the pi bond, how I'm addressing that lost pi bond to make a bond to that hydrogen. And I'm going to move these electrons back to that oxygen. So notice I'm addressing everything, the bonds forming and the bonds broken with those two arrows. Now, I do want to take a look at this positive charge. Why does that carbon develop a formal charge of +1? Well, it had a full octet before, but it lost that pi bond. In order to do this step, in order to do this transformation, it lost that pi bond around it. And that's why it developed a formal charge of +1. All right, look at all of this stuff. It's very easy to kind of go cross-eyed here, especially when it's like, you just expect me to draw all these, arrows for all this stuff. Well, again, all I'm asking you to do is look at what has broken and what has formed. So let's just focus on this first reaction. Okay, well, what's new? Um, well, I got a new bond here between nitrogen and phosphorus. That's new. And what else has changed? Well, this used to be a nitrogen-nitrogen double bond. Now it's a single bond. Okay, well, let's draw something that addresses that. So I'm going to make a bond from the phosphorus to that nitrogen. Now, if I do that, nitrogen, this one right here, will violate the octet rule. So I'm going to fix that by moving these pi electrons to that nitrogen. And notice that explains both things that happen. There's a new phosphorus nitrogen bond, and then the nitrogen nitrogen double bond went to a nitrogen nitrogen single bond. Okay, so let's look at the next step. Okay, let's address what happened here. So what this above the reaction arrow is saying is it's kind of telling you, it's kind of cluing into what's happening, is that nitrogen left, diatomic nitrogen left. That minus N2 is kind of saying it's like subtracted out of the problem. So what nitrogen atoms are we talking about? There's like three of them. Which two left? Well, it's got to be these two. Okay. Now I have two ways I can do this. I can either, let's, let me show you the wrong way here. Now, why would this be the wrong way? Why not just have that leaving group leave like that? Break that bond between these first two nitrogens. Okay. If electrons were to leave around this nitrogen I'm putting a circle on, what charge would it develop? I should see in the product a nitrogen with a plus charge, but I don't. I see nitrogen with a minus charge. So drawing the arrow like this is not the correct way. I'm going to do this. Because by demonstrating that, now I get to nitrogen with a formal charge of -1. Okay, let's take a look here at this next step. Again, I want you to pause the video and ask yourself, what happened? How is this product different than these two reactants? Okay. Well, one of the kind of obvious things is that I connected the two reactants together. Well, where did I connect them? I took a nitrogen here and I connected it to that carbon. Well, how does it do that? Why does it do that? Well, I got nitrogen with a minus charge. That's a really good nucleophile. I have a carbon oxygen, a polar carbon-oxygen bond. That makes an electrophile. So I'm going to do a nucleophilic attack. That's going to connect the nucleophile to the electrophile. And so that I don't violate the octet rule, I got to move those electrons, those pi electrons, up to the oxygen. That's how we get this oxygen here with a negative charge. Here's my new nitrogen carbon bond from that nucleophilic attack. Okay, let's go to the next step. Again, pause the video and ask yourself, what happened? What is different? So we take a look here. What's one thing that's different? Well, this was an oxygen carbon single bond. Now it's an oxygen carbon double bond. Okay. What else is different? Well, this oxygen here used to be attached to a carbon, but now it's no longer attached. So let's draw some arrows that address that. I'm going to take these electrons, move them down to form that double bond. Now, if I do that and just leave it, what would be so bad about that carbon I just put a red dot on? It'd have too many electrons to it. So I'm going to do a common mechanistic step, have a leaving group leave, and now that oxygen is no longer bonded to that carbon anymore. The oxygen in green, that bond got broken so that there isn't any violation of the octet rule. All right. Well, let's kind of take a look at what is happening in our next step. So again, pause the video. I want you to physically write down what you see is different. Can you identify what bonds were broken and what bonds were formed? Okay, so let's highlight some different things here. Well, first of all, this oxygen right here is now bonded to that phosphorus group. Okay. There's no longer a bond to the nitrogen, that phosphorus nitrogen. And a lot of stuff has changed right here. Okay, so let's draw some arrows that explain that. One of the things that should jump out at you is you got an O minus. Okay, I circled it there on red on the right. And I got a positively charged phosphorus. What do you naturally want to do if you see something that is a negative charge? Call that a nucleophile. Something that has a positive charge, call that an electrophile. Well, let's do a nucleophilic attack. Let's make a bond from the nucleophile to the electrophile. Now, if I do that and leave it, I would violate the octet rule for phosphorus. So I'm going to take these electrons. Instead of moving them back to the nitrogen, though, I'm going to use them to explain how I get a nitrogen carbon double bond. This double bond right here. And then, so that, again, I don't violate the octet rule for carbon, I'm going to move these pi electrons up to that oxygen. All right, and then finally, With this last step, again, ask yourself, what is different? What happened? What bonds broke? What bonds formed? Okay, so let's identify some things. Well, first of all, this carbon-oxygen bond here is now a carbon-oxygen double bond. One of the more, the biggest things that happened is that this whole group has left. That's what that's explaining above that reaction arrow. It's basically saying that that whole phosphorus group is leaving. Kind of clues you in, like you got a leaving group leaving here. So let's draw a mechanism that explains this. I'm going to move these electrons down to form the double bond. So look at the product there I highlighted in yellow. That red arrow describes forming that double bond. And because I don't want this carbon right here to violate the octet rule, I'm going to break this bond, and that's how I get this phosphorus oxygen double bond there. So this is demonstrating a leaving group leaving. All right, finally, let's do one more. Okay, so again, with each of these steps, you need to identify what has happened. All right, well, one of the big things here in this first step is I got a nitrogen with a hydrogen on it, and I got an oxygen missing a hydrogen. What do we call that when a hydrogen goes from one thing to another? That's a proton transfer, a Bronsted-Lowry acid-base reaction. So you should have that ingrained in your mind, already. The base is going to use its lone pair to pick up a hydrogen. Uh, and then the electrons here go back to the atom it was attached to. All right, let's look at the next step here. Again, pause the video, highlight what has changed. Well, one of the big things is that this oxygen, oh, sorry about that. This oxygen is now attached to this carbon. And this pi bond has resulted in no longer being there, and now there's a lone pair on that nitrogen. So let's draw a couple of arrows that will demonstrate this. This oxygen is going to form a bond to that carbon, and I move those pi electrons back to the nitrogen. Okay, and the next step, again, once more, you're going to get tired of me saying this, but pause the video and write down what you see is different. Okay, so probably the only thing is I got an oxygen with two hydrogens on it. And now that hydrogen is transferred elsewhere. This is just a proton transfer. I'm going to use the lone pair on this water to pull off a hydrogen and move these electrons back. Hopefully you're kind of noticing that these patterns that I talked about earlier are being used over and over and over again. There's very few like really unique mechanistic steps. There'll be some weird things out there every now and then, but most mechanisms you're going to draw will incorporate a combination of those four templates. Now, um, if we take a look at what has happened here, So the big thing is that this nitrogen got another hydrogen on it. Well, how do we describe that? We're taking a proton from this hydronium here. So this is again another proton transfer. Okay, now this one might take a little bit more viewing. So again, pause the video and outline everything that has happened. So what's one big thing? Well, this nitrogen is no longer attached to that carbon there. So used to be attached to that carbon, and now the nitrogen is no longer attached. What's the other big thing? Well, there's now an oxygen carbon bond, a double bond, I should say, right there. So how do I describe all of this happening? Again, remember the basic foundations of mechanistic arrows, they always have to start at electrons. So I'm going to use a lone pair to form that double bond between the carbon and oxygen. And so that I don't violate the octet rule, I'm going to move I'm going to break that bond and move those electrons back to the nitrogen. And then finally, to wrap this up, again, ask yourself, what happened in this last step? Well, the major thing here is that this oxygen no longer has a hydrogen on it. So how do I describe that? I'm just going to do a proton transfer. This oxygen will pick up a hydrogen. This is an acid-base reaction. I move those electrons back to the oxygen, and I've done my proton transfer. So that's going to conclude this unit. I highly recommend doing as many problems as you can. You have to practice this. There's no way you can do this just kind of naturally. You have to practice it, do it over and over and over again. The more problems you see, the better you're going to get at this.